I just want to clarify one point. Now, when we said we are always talking about c being the speed of light, c is actually a fundamental constant. Of nature, of the universe, in fact. Just like the Newton's constant, the h bar, just like they are constants, c is a constant. And it just turns out that light moves with this constant in vacuum. So one of you were asking what happens if we have a medium. Well, nothing really changes. Because whenever we are talking about the speed of light, we are not talking about the light actually. We are talking about this fundamental constant. If there is a medium, well, fine, then light is not moving with this fundamental constant, but this fundamental constant is still the same. The medium doesn't change this fundamental constant. It just changes whether light moves with a speed equal to this fundamental constant or not. So all our treatments over here still hold. Now, any questions on this length contraction?
The reason I asked the size of the particles, I was wondering if this length contraction is relevant in any scientific measures.
Sure. You see, we are colliding ions. In LHC, for example, especially we are colliding lead ions. And when they are moving very close to the speed of light. And when you are trying to make estimates about their properties, what will happen, we don't imagine spherical nuclei. The nuclei that are colliding in LHC have this shape. Because of length contraction. They are very narrow. So we should take that into account.
So actually C is the speed of light in vacuum, right?
Well, the more precise way of putting it is that the speed of light in vacuum is equal to c.
Okay. So in this case, can we say that time for a photon in vacuum is undefined, and length for a photon in vacuum does not exist?
Well, let's say the universe, the three-dimensional universe, let's say, for the photon is actually two-dimensional. Because you see, if the photon is moving in that direction, it's not aging, its time has stopped. Plus, the size of the universe in that direction is 0,
Yes.
but not in the other direction.
I was talking about. So what
But
about time?
time stops.
Time stops for it. Okay.
But we will never be able to talk about, if we move with the photon, we will never be able to.
Hocam tek konusu fazla dağıtmak istemem ama sanki hocam ışık hızıyla evrenin genişleme hızı arasında bir sıkıntı vardı. Yani öyle şeyler hatırlıyorum bir de. Böyle sanki evrenin genişleme hızı ışık hızından daha fazlaydı. Hatta o yüzden bazı karanlık bölgeler kaplandı.
Okay, that is true, but I mean, do you mind if we continue these discussions after the lecture? I mean, there are many blackboards around. We can continue there.
Şey sormak istiyorum. Bu şeyi de bozmuyor mu? Hani fizik yasaları evrenin her yerinde geçerlidir şeyinde mi?
No. You see, okay, I'm trying to avoid general relativity, but you are trying to go into general relativity. You see, one problem your friend was mentioning is that we look at the universe. There is a microwave background radiation, which corresponds to something like 2.7 Kelvin. So when somebody tells you that the space is not at 0 Kelvin, but the temperature of space is 2.7 Kelvin, what they actually mean is that it's this microwave background radiation. And that is something we will study, by the way, when we discuss the black body radiation. How do we get this 2.7 Kelvin? But then there is a problem. If you look at the universe in that direction and the universe in that direction, they have the same temperature, more or less. The deviation is very small. But that part of the universe couldn't have yet influenced that part of the universe. So they can, if you talk about the cause and effect, I mean, these two parts are completely independent. That part is not in the past of that part, in a sense. They shouldn't be influencing each other. But if they are not influencing each other, how come they are at the same temperature? There's no need for them to be at the same temperature because they couldn't yet communicate. So it's just like you are picking up a random number at home and your other friend picks up a random number, another random number at home, at his home, and you don't communicate with each other and you just realize that you have picked up the same number. So it's just like the universe had picked the same temperature at completely unrelated regions. Now, one way to explain this is that the expansion of the universe. But of course, we have to assume that the universe should have expanded faster than the speed of light. So that these two regions were able to communicate in the past, but then they moved faster than the speed of light, and now they are unrelated. But then you will complain, how come they can move faster than the speed of light? We will say many times that nothing can move faster than the speed of light. Now, the distinction there is that what general relativity does is that it describes the universe as let's say, a large balloon. Just imagine a balloon. If we were in two-dimensional, if the space was two-dimensional, you can just model it as the surface of this balloon. And let me also imagine that we are blowing up the balloon. This is the typical. Yes. Well, there are actually two different kinds of speeds we should be paying attention to. One is my speed relative to space at my position. And the other one is how fast our separation is increasing. These two things are not necessarily the same thing. Just imagine a balloon, and you put some dots on the balloon. Those dots might be at rest on the surface of the balloon. Okay? But if you blow up the balloon, although these dots are not moving on the surface of the balloon, their separation will increase. So imagine instead of fixed dots, there are ants on the balloon. Well, the ants will be able to move, 1 kilometers per hour. That will be their maximum speed. So if there are ants, the fastest that their distance, if you have the balloon, you are not blowing up the balloon. If these are ants, their separation can at most separate by 2 kilometers per hour. But if the balloon is expanding at the same time, then their separation can be increasing much faster than these 2 kilometers per hour. So there are basically two speeds over here. Well, two different concepts. One is the speed of the ant relative to the surface of the balloon. The second one is the expansion of the surface itself. Now, when we say that in special theory of relativity that nothing can move faster than the speed of light, what we are actually saying is that in the analogy with the balloon, the ants cannot move faster than the speed of light relative to the surface of the balloon. But that doesn't mean that the distance between two objects cannot increase faster than c times time. This separation can increase faster than the speed of light. There is nothing that restricts that. But each one of them separately cannot move faster than the speed of light relative to the surface at their position. Well, we will come to that, but there are some other things we have to discuss before. If you also follow the historical development, first it was the speed of light. It was actually the speed of light. But then we realized that it's not really the speed of light itself, but rather some fundamental constant of nature. And the light turns out to be moving at that speed. in vacuum. Other questions? Okay, let's go to the Lorentz transformations. Well, I'm kind of changing the order of the subjects in the book, but I would rather follow your questions than follow the book. We will just complete whatever we had skipped. Yes, I will, hopefully. So now, before going to Lorentz transformations, what we are aiming at, you see, if we stick with three-dimensional coordinates, let's say I have some axis, x and y, and then your friend chooses some other axis, x prime and y prime, and then we have a given point. There is this point. Well, your friend will say that that point P has the coordinates Px prime and Py prime. So this point P R will be Px prime in the x direction plus Py prime in the y direction. But I will say that it has the same point has the coordinates Px in the x direction and Py in the y direction. Now these are x primes. Px in my x direction plus Py in the y direction. And in fact, these two expressions, although we have different components, different x and y components, they are the same thing. Now, how are they related? Well, I can say that Px prime is just r times x, a unit vector in the x prime direction. But r is also this quantity over here. So Px prime is actually Px times x dot x prime plus Py y dot y prime. And let's assume that these two coordinate axes are rotated by the angle theta. You see, x hat vector is this vector, x prime vector is this vector. The scalar product is just the product of the magnitudes, which is just 1 times the cosine of the angle between the two. So this is Px times cosine theta plus Py times no, sorry, that's not y dot y prime, that is y dot x prime. Well, these are vectors with unit norm, so the y hat times x prime is just the angle, the cosine of the angle between the two, so it's cosine pi over 2 minus theta. So Px prime is Px cosine theta plus Py sine theta. And if you like, you can also calculate Py prime, which will turn out to be minus Px sine theta plus Py cosine theta. So this is, in a sense, is my dictionary. If I measure the coordinates Px and Py, and your friend wants to compare it with his results, he just needs to put my Px, Py over here, obtain what he should be measuring in his own coordinate axis. And that's exactly what we will do with this in special relativity now. So we have, rather than just rotated axes, we have two different reference frames. Pi over 2 minus theta. It is just this angle over here, pi over 2 minus theta. So what we will do is we will take an event, the same event, and we will just try to find some translation between the positions and time measured in one reference frame with the position and time measured in the other reference frame. And after that, remind me about the vertical length contraction. I forgot that. Anyway, after this. Okay, so I will assume that I don't want to deal with translations. At t is equal to 0, I have two reference frames. At t equal to 0, they overlap. Their origins overlap. X, y, x prime, y prime. Now, let's assume that the event happens over here. And the O prime observer measures that event to happen at the time t, at the time t prime, at the x coordinate x prime. For the time being, I will not be worried about the y and the z coordinates. Just the x. The O prime reference frame is moving in this direction with a speed v. Well, I can always choose the direction x-axis to be in the direction of the speed. So I can, without losing any generality, I can just assume there's no y or the z components of the speed. And the same event, the O observer will measure that it happened at the time t at the point x, at the point with the x coordinate x. So how will we be able to translate the two? That will be our question. Now, for observer at O, well, this distance is x prime, as measured in the O prime reference frame. So the O observer, we'll see that that distance is just O prime times square root of 1 over 1 minus v. No, that distance is x prime times square root of 1 minus v squared over c squared. I'm trying to write x. Now, x should be this distance measured by this one. And he will say that it is just, it's moving with a speed v for a time t. It should be v times t plus this distance, the distance of x prime from the O prime, but he knows that the observer in O prime had measured it to be x prime. So in the O prime reference frame, that distance is x prime. But that means that in his reference frame, that length should be contracted by by this factor. So this is the distance. So x should have this form. Now let's look at the observer O prime. Well, for the observer in O prime, O is moving in the opposite direction with minus, well, let me just draw it also. This is moving with a speed minus v. He knows that, well, this point is at a distance minus vt in the opposite direction. It's minus vt. He knows that O observer had measured this distance to be x. But he will see that the distance contracted. So it will be minus vt plus x square root of 1 minus v squared over c, or 1 minus minus v squared. So the observer in O prime concludes that x prime, sorry, this is t prime. X prime, t prime, and x should be related by this relation. And observer in O concludes that xv and xt and x prime should be related by that relation over there. Well, we have, what we are trying to do is we are trying to relate x and t with x prime and t prime. Well, these two are enough. So let's try to find x prime and t prime in terms of x and t. We have two unknowns and we have two equations. Well, the first equation, let's say this is 1, this is 2. The first equation tells me that x is equal to 1 over square root of 1 minus v squared over c squared times x prime plus vt prime. This is this equation. Let's go to the second equation, and from the second equation I will solve t. The second equation tells me that t is equal to 1 over v x minus x prime times square root of 1 minus v squared over c squared. But I already know what x is in terms of x prime and t prime. X prime plus vt prime minus x prime square root of 1 minus v squared over c squared. Well, let me simplify it a bit. 1 over v. If I take into parentheses of x prime over 1 minus v squared over c squared, I have 1 minus v squared over c squared. Plus vt prime over square root of 1 minus v squared over c squared. Well, this minus cancels this minus. Now this 1 cancels this 1, minus makes a plus. I have 1 over v over here. It cancels one of the v's here and also the v over here. So t is just 1 over square root of 1 minus v squared over c squared x prime, now t prime, plus v over c squared x prime. Well, this part is just the algebra. You have two equations for the two unknowns x and t. We are assuming x prime and t prime are known. We just want to translate them into x and t. You have two equations for two unknowns. If you solve for them, this is what you get. Well, most of the time you define this 1 over the square root of 1 minus v squared over c squared to be gamma. To simplify this calculation, this expression, so x is equal to gamma x prime plus vt prime and t is equal to gamma t prime plus v over c squared times x prime. Now also keep in mind what these transformations are. I am one observer, one reference frame. There is another reference frame moving in the positive x direction with a speed v. In that reference frame, one observer at rest in that reference frame measures the time of an event to be t prime and the position of that event to be x prime. And at t equal to 0, our origins overlap. So when my watch is t equal to 0, that reference frame was right over here. And at that time, he also set his time t equal to 0. So t prime is equal to 0 and t equal to 0, they match. Then, of course, he continued. So he measured the event to be happening at the point x prime at the point t prime. If he had measured the event at the point x prime at the point t prime, then I have measured exactly the same event at the point x and at the time t. This is what these equations are telling me, how to go from one reference frame to the other one. You see, one of you were asking during the break, why do we call the time the fourth dimension? Now, if you go back to this example, this simple reminder, let's say, if you just change your axis, the x and the y components, they just get mixed up. So you cannot really say that some quantity is purely x. Okay, it might be purely x in one coordinate axis, but not purely x in the other one. Now, if you look at these Lorentz transformations, if you go from one reference frame to the other reference frame, x and t, they also get mixed up. It doesn't really make sense to talk about a pure time or pure position. According to whom? If you identify something as pure time in one reference frame, it will be a mixture in the other reference frame, and all reference frames are equal. So in that sense, it doesn't make sense to separate the position and time as two independent quantities. Any questions on these? Now, of course, I didn't write it over here. Y is equal to y prime and z is equal to z prime. Y and z are the distances in the vertical direction, in a sense. Now, why doesn't the distances in the vertical direction contract? The thought experiment to prove is this one. Let's imagine a thought experiment. There is a train. Let's say I am the train. I'm just moving in one direction. And somewhere along the line, I'm a passenger in the train. Somewhere along the line, there is something to put some marks. Now, in the reference frame of the station, this is at rest. There is this wall. I'm just moving with some speed v. And no, let's just imagine this one. Let's just imagine there is a mark at this height, right over here. And I keep there's a pen in my hand exactly at the same height. In the reference frame of the station, let's just, for the sake of argument, assume that in your reference frame, if I'm moving in that direction, there is a length contraction in the vertical direction also. So what will happen is, if we assume that there is a length contraction in the vertical direction, as I move, you will see my vertical height to be contracted. So this height will be over here. So I should be marking below that line as I am crossing. Do you agree? But now let's look at the reference frame of the train. I am at this height. I am at rest. That is moving. The line is moving. So as it's passing me, it should go down. It becomes smaller, shorter, if there is a contraction in the vertical direction. So since it becomes smaller, when it passes me, I should mark above the original line. Then we stop the train, we go and look. Where do I mark? Do I mark below or above? There can be only one mark. And since the two observers cannot agree, no matter what they do, it cannot go below or it cannot go above. It should be exactly at the same height, which just shows that there cannot be any length contraction. You see, contrary to twin paradox, in the twin paradox we could argue which observation we will see, because one reference frame was a non-inertial reference frame. In this example, we can always cook up the system such that all the observers are always in the same inertial reference frame. Yes? Is? Well, you see, we are moving with the same speed in the sense that if I am moving with a speed v according to you, and you are moving with a speed v according to me, and just in the opposite direction. If you look at the two equations we are over here, you see essentially the same thing happened. These two equations are identical equations with the exchange of the coordinates and change of the sign of v. But this factor, the gamma factor, doesn't depend on the sign of v because we are taking the square. Since gamma factor is the same, the length contraction should be the same, if there is any.
If you imagine going in this direction, if length contraction and vertical direction happen, could we pass maybe speed of light even if we did bump a little bit in vertical direction, since that length is contracted now?
No.
According to an outside observer.
Now let's look at how do we add the speeds. Okay. So you are basically saying that, okay, we are moving very close to the speed of light. So if I move my hand vertically upward, will my hand be moving faster than the speed of light?
No, I'm not
No.
meaning that. We are moving.
Okay.
Imagine the length contraction vertical axis happens.
It doesn't happen.
I'm trying to say if that happened, it would change something. Yani şeyi kastediyorum hocam aslında. Biz bir yönde giderken o aslında dışarıdan o yönü kısalmış olarak görüyoruz ya.
Okay.
Öbür yönde kısalıyor olsaydı çok az bir hızlanmayla o aksiste çok uzun mesafeler kat edemez miydik? Yani
But it doesn't happen.
Katmış olmuyor.
I don't think so. I mean, you might try to cook up, but I don't see why, how. It just doesn't happen, anyway. Other questions? Let's add the speeds. Okay, and then we will end today's lecture. Well, let's see. What is the speed of an object? The x component of the speed of an object for one observer. Well, the change in x divided by the change in time t. This will be the speed, Vx. Which should be equal to, if we just look at this gamma factor, assuming that we are following an event, following an object. So we just have two events. We measure its position at one time. We measure the position of it at the successive time. So we have this delta t, we have this delta x. Well, this delta x will be related to delta x prime and delta t prime in the other reference frame, by that relation over there. So delta x will be just gamma delta x prime plus v delta t prime divided by, and delta t will be gamma delta t prime plus v over c squared times delta x prime. Gamma factors, they will cancel. I can divide the numerator and denominator by 1 over delta t prime, which will just give me Vx is equal to delta x prime over delta t prime plus V divided by 1 plus V over c squared delta x prime divided by delta t prime. Well, this is nothing but Vx prime plus V divided by 1 plus V over c squared times Vx prime. Again, I repeat, this V is also in the direction of x. And this is how the speeds in the direction of the relative speeds of the reference frames adds up. Well, what about the y component of the speeds? Will they change or not? You see, there is one reference frame. There is the other reference frame, which is moving relative to me. And he measures the vertical component of some object. I also measure the vertical component of the speed of the same object. Will we agree or not? There is no length contraction in the vertical component. So the speed should be the same.
Time difference?
There is a time difference, though. So let's see, Vy, which is delta y divided by delta t. Delta y is the same. There is no vertical length contraction, but there is a time dilation. Delta t is just gamma delta t prime plus v over c squared delta x prime. So again, we divide the numerator by denominator by 1 over delta t prime. So we get Vy prime divided by gamma 1 plus v squared, v over c squared Vx prime. Where? This is delta t prime.
Other side of the plus side. Yeah.
This one. 1. Okay. Don't worry, soon you will learn to decipher my handwriting. So you see, the y component also changes. And I remind you again, this is the x component of the object, the speed of the object. The change in the y component depends on the change in the x component of the x component of the speed of the velocity of the object. And similarly, Vz will be delta z over delta t. If you just do the same derivation, it will be Vz prime divided by gamma 1 plus v over c squared times Vx prime. Now let's do a very simple example. Assume that v, the relative speed of the reference frames, is equal to 0.999 c. And the observer in the other reference frame measures the speed of an object to be 0.999 c. Almost the speed of light. And the y component, z component are 0. Now this is Vx primes. These are measured by the other observer. So what will I measure its speed? Vx will be, well, the addition law is Vx prime plus v. This is Vx prime is 0.9999c plus 0.999c divided by 1 plus v is 0.999c divided by c squared times 0.999c. Put in the numbers and you will find that this is less than c. Even if you put c here, even if you take this one to be c, this one to be c, this is c, this is c, so you have 2c, 1 plus c over c squared multiplied by c, it's just c. Even if there is an observer moving at the speed of light, he observes something else moving at the speed of light even further away, I will still measure the speed of that moving object to be at c. It will not be faster than c. Any last questions? If you like, we can continue also outside. Now, I am the observer. I am looking at the other reference frame, and that reference frame is moving with the speed 0.999c. And that observer sees the object moving with a speed 0.999c even in that direction.